Okay, so we'll come to the last day of of text, speech, and dialogue, and we have the invited speech of Anna Rogers, who supposed to be here, but due to some personal problems, she will have the presentation remotely. So, Anna, you can start.
Thank you. Thank you for the introduction. Thank all of the organizers for inviting me. And I really wish I could be there in person. I'm sure the weather is much better in Czech Republic than in Denmark. But here we are. Let me start by stating perhaps the obvious. I guess we can all agree that at the moment the field of natural language processing is in a bit of a evaluation crisis, especially in the tasks which we call the NLU, the natural language understanding tasks. The problem is that we come up with better benchmarks at a pace which is not enough for the pace that we solve those benchmarks. And as a result, we have the situation in which, for example, happened with CoQA dataset. I was in NACL when this paper was presented, and as with many data and benchmark datasets, one of the claims was that this is a challenging task which the current models cannot solve very well. And basically, by the time that the authors got to present this paper at NACL, it was solved. And this is far from being the only case like that. So unfortunately, it does not mean that we actually have solved either question answering or reading comprehension. If you use any voice assistants which rely on that technology to provide you answers to your questions, you will know that you can't always trust them. In this case, Google Assistant gave me this answer to the questions: who won and who lost the Infinity War. And that's despite, the answer is the same, despite the fact that it actually had the information in the snippet to deduce that the good guys lost. So the first sentence here says, unfortunately, the good guys suffered the greatest losses. So technically it could at least have tried to do that, but no. Another recent example is with GPT-3. This is from a piece by David Bender and Douglas Hofstadter, who asked GPT-3 a nonsensical question. When was the Golden Gate Bridge transported for the second time across Egypt? To which it confidently stated that that happened in October 2016. That also shows that no, we have not solved question answering yet. So I would argue in this talk that part of the problem with this evaluation crisis is how we define our NLU tasks to begin with. Theoretically, there's two ways to do that. We can either do this intentionally based on some theoretical constructs. We say what exactly we mean. We specify the conditions for when we say that the performance of the system is good enough, based on some theoretical conditions and conceptualizations. And the other is the way we always do it, by just providing some sort of X to Y mappings, which the model has to learn. And then we say that whatever it learns constitutes the task of reading comprehension or translation or question answering. And here is an example of how that has often been done in the era of the crowdsourced data sets. This is the famous squad instructions that the crowd workers were given. Basically, they were just told to read the paragraph, to ask a certain number of questions, to select the answer and to try to avoid using the same words as in the paragraph, and to try to pose hard questions, whatever that means. So none of this is specified. Although Squad has been the benchmark for question answering research for many, many years, basically what was meant by question answering or reading comprehension in this case has only been defined like this. Of course, as a result, when we test our models more thoroughly, we find that they often fail on things that they should not fail as a system that can actually answer questions or comprehend what it reads. So these are examples from the behavioral testing paper by Ribeiro and colleagues. And what they found was basically that if you perturb the questions in a certain systematic way, then you will find that the performance on the perturbed questions will not be as high as you would hope, even though the capabilities seem rather basic linguistically, such as the ability to do comparisons or negation or map intensifiers to superlatives. So this is something that we have known for quite some time, but yet we keep defining the tasks, the NLU tasks in the same X to Y mapping way. And it is becoming apparent that this claim of generality that comes from the underdefined problem, that will often act as a cover and allow us to say that we have solved question answering or reading comprehension when in fact we have not. And it allows people to generate loud headlines without reporting the limitations which the model certainly has. One of the proposed solutions has been the adversarial data collection, the approach in which you ask people to generate such questions that the model cannot answer. I would argue that this is not a solution either, because it doesn't address the core problem, which is that we don't know what kind of questions the model can answer. We didn't know this before, and we still don't know this after the model has been provided with more hard examples. We just know that on some grand average, it is doing better than it did. So all of this puts us in a position in which we as a field are at a crossroads. We can keep doing what we have been doing, specifying tasks with X to Y mapping, and hope that the model will somehow figure it out. Or we can do the data work and say what exactly we would mean by reading comprehension or question answering. And I have a position paper arguing for the latter. And in this talk, I'm going to share some empirical and theoretical work towards providing such better definitions and evaluations. And the first part of this work deals with the question of what questions we have been actually asking. So if you pick up any paper presenting a question answer in your reading comprehension dataset, you will find that it will typically have a qualitative analysis section. And what happens there is that a small sample of crowdsourced questions will be analyzed by the authors with the categories that they saw applicable to their data. And those categories will be completely different in different papers. So for Squad, they talk about synonymy and world knowledge and syntactic variation and multiple sentence reasoning. For News QA, as another example, it's word matching and paraphrasing and inference and synthesis. And for Hotpot QA and multi-hop dataset, they talk about bridge entities, comparing two entities, reasoning that requires more than 2 supporting facts, other kinds of reasoning. So all of this is, of course, completely different, and so makes it hard to compare different data sets in terms of what kinds of questions they actually contain. So we have just finally got final acceptance for this paper, which will appear in ACM CSUR. And what this paper does is provide a broad categorization for the kinds of distinctions that people have been making in question answering and reading comprehension literature, for the kinds of questions, for what format the question and evidence is in, for the languages, for the domains, for the target skills, whether the questions are information seeking or probing, etc. So, for example, we discuss whether the questions have been natural information seeking questions or probing and everything in between. We discuss what are the possible question and answer formats, how much evidence is provided, whether it's single source or multiple sources or no sources, and the model is supposed to come up with all the information by itself. We discuss what languages have a lot of resources and which ones don't, which is most of them, of course. How is the multilingual work going, mostly with industry backing, and how important it is to have more monolingual work on languages other than English. We discuss the great confusion with the term domain, which people use both as genre and topic, and all the data sets that come in these distinctions. And most importantly, we came up with this taxonomy for the skills which the questions are supposed to test. And the core feature of this taxonomy is that, well, as you can see, it has 5 axes: world modeling, retrieval, inference, multi-step, and input interpretation. And these axes are all supposed to be independent. So the same question, of course, you need to understand the lexical information, you need to understand the syntactic form to even be able to interpret the question, but at the same time, it can involve aspects of world modeling. You may have a challenge in retrieval, you may have a certain inference step, etc. So all of this is orthogonal. And then within those axes, there are further subdivisions. And of course, this is only a brief scheme. There are a lot more sub-skills which do not fit in here. But we believe that of all the over 200 data sets that we have looked at, this covers the kinds of questions that people have been asking. And it's not quite, you see that one of the options for retrieval here is the answerability, and the questions can be invalid. And in fact, we found at least 9 ways in which questions can be unanswerable, as opposed to just 1 in Squad 2.0. So questions can be rejected by a human speaker because they have invalid premises, because they're not specific enough, because they have missing information, a problem which is actually quite frequent in data sets such as natural questions, where the search engine queries are provided with the assumption that the browser already knows where you are and will provide you with the answer relevant to your location only. Some questions just don't have answers. Some questions don't have consensus on the answer. Some questions are uninterpretable semantically or in general. Some questions rely on the wrong model of the world. Some questions are rhetorical. And some questions just don't make any sense. and wouldn't be useful to answer. So, okay, all of this is for the kinds of questions that people have been asking. Now, of course, the problem is how do we now get question answering data that would target a specific skill, such as coreference or world modeling or meta discourse or whatever else that we are interested in. And the next thing I'd like to show is a case study in trying to collect a data set for which we would collect specific types of questions, and we would know where they are so that the data set would be used for both training and diagnostics of the trained model. In this case, the data set is called Quail, and it has a 4x9 design. So there were 4 domains: fiction, news, user stories, and blogs. And in each genre, we had the same number of texts, about 100, and for each text, we were asking the same 9 kind of questions. So that gave us about 15,000 crowdsourced questions. And to the best of my knowledge, this was the first data set to combine text-based, unanswerable, and world knowledge-based questions. To show you what I mean, these are the types of questions that we had. And some of them are based strictly on the information in the text. So for example, temporal order, you have to know the specific situation, and that's the only source in which you can possibly find the right answer. In the world knowledge-based questions, you do need to also take into account the context, but it is also helpful to know that in this case, for example, generally if people fall down, then they end up on the ground and not in the sky. And that is a world knowledge fact. And finally, the unanswerable questions, at that point we didn't know any better and let people ask any kinds of unanswerable questions. But the correct answer for this kind of question would be not enough information to answer this question. And this is also the answer option that would be available to the model for all the other question types as well. So this is a multi-choice data set, as you can see, and there's always 4 answer options, and one of them is not enough information. Okay, so this is what the data looks like. We collected it. We tested a bunch of different kinds of models. We found that BERT was doing the best, but still the data was challenging because the random baseline, of course, would be 25% accuracy, and BERT got 56%. So kind of good enough. And then we started looking a bit further, and we created a challenge set. And the challenge set is a set in which the same questions that were crowdsourced were then rewritten by the authors so as to decrease the amount of lexical overlap of the same words being used in the question and the text between for about 500 questions. And as you can see, the performance drops quite a lot on different categories for different models, but for BERT, sometimes up to -40% for belief states. And that means that even with all this effort to create a very diverse data set with 4x9 design, with four domains, with different kinds of questions, still the model learned to rely on lexical overlap as a heuristic to tell how to answer a given question. The good news is that just in terms of the crowdsourcing methodology, we found something like Hawthorne effect, So Hawthorne effect is this effect when people behave differently when they know that they're being watched or checked. I think the original study was that if people see a poster with human eyes looking at them, they are more likely to wash their hands better. So in this case, what we did in the first iteration of our data crowdsourcing, we just asked people to write a specific type of question and just provided them with instructions and examples, as everybody does. And then, of course, we found that people were not writing the right kind of questions, but whatever they felt like. So we introduced some simple JavaScript-based checks. For each question type, we collected, based on several rounds of crowdsourcing, some typical keywords that could be expected to be in a given question. So for temporal order, that would be words like before, believe, before, when, after, in what order, such things. And if we found that the crowd worker did not use any of those words, then we would show a pop-up asking, are you sure that this is the right kind of question? And that did improve the likelihood that the question was of the right type. At the same time, even with all this effort, clearly our data still had artifacts. So in this case, I'm just showing performance of BERT broken down by different domains. And you can see, for example, that for news, its performance on unanswerable questions is quite high. It's almost 70%. And that's a lot better than on the blogs. And that means that there's something in the unanswerable questions on news that makes it easier. And that's likely an artifact of the fact that, for example, the news text was easier to copy paste and harder to paraphrase than other kinds of text, for example. So basically, that means that even with all this effort to create more diverse data, we are probably going to end up with 36 sub data sets with their own artifacts and spurious patterns, and not with an artifact-free diverse data set that we would like to see. And that is, of course, disappointing, but a useful lesson to learn. All right, so if diverse data by itself is not enough to get BERT to do what would merit the term reading comprehension, then how do we even tell what it is doing? And when do we tell that it is doing the right thing? And I'm very excited to share this study with colleagues at the University of Copenhagen, which is going to appear in Calling this year. And what we do in this study is kind of challenge the idea of when we would say that the model understands anything. And we are, of course, not the first people to question that. From the early days of good old-fashioned AI, there have been people who were saying that we should not even use terms like understanding, that this is a misnomer where the models are concerned. And more recently, there's a great paper on the topic, why AI is harder than we think. So I'd like to start with a few general points on human understanding, which make it unlike anything that currently happens in NLP. And the basic fact is that our understanding depends on our set of conceptualizations of the world. We can call it the linguistic worldview, the picture of the world, the Umwelt, and all of those conceptualizations, they come from our personal experience. And as we learn and understand more things, our set of pre-existing conceptualizations is updated. So this much I think is uncontroversial. And to understand something, we generally need a suitable set of conceptualizations. Aristotle was certainly a very smart man, but for him to read a modern quantum physics textbook would be quite hard, just because he didn't have the right set of conceptualizations at that point of time. I can't read a modern quantum physics textbook. Okay, then what follows is that pre-trained language models do not represent a picture of the human world, at least because of the experience that they have is different from the experience that we humans have. Furthermore, they don't have a failure mode. So if I don't understand something because I don't have a suitable set of conceptualizations, I know that I don't know. And the encoder will still encode even if its weights are completely random. Now, humans, it is true that humans may and do avoid the process of full comprehension of texts when the information needs can be served by some heuristic strategies. And we could talk about this as slow reading versus fast reading to mirror Daniel Kahneman's slow thinking and fast thinking. Definitely, as students, as consumers of news, we do not always engage with every text that we encounter in the slow way. But the reason we do that is because we need to save cognitive effort. We get tired, models do not. So generally for the models, we do expect them to actually be better than us and to do the full comprehension, which would lead to the maximum accuracy whenever possible. So I would argue that instead of asking the question, does my model understand language? Perhaps a better question to ask is, does my model produce its output based on valid information retrieval and inference strategies? To test whether that is happening, what we argue in this paper is that we need 3 steps. One is defining what exactly should be understood. Two is testing whether the model is making the decision for reasonable reasons, the reasons that are likely to actually bring you to the correct conclusion across board in different cases. And there's plenty of evidence about how this is not the case with the current generation of models. And this brilliant paper by Sako Sugawara, they show that you can replace every word in Squad with a nonsensical ID, such as add1 and noun 17, and fine-tune the model on that, and it will still get F1 of 61 on the corrupted development set. So whatever it's doing, it's not learning anything about language. And step 3 for testing, for being able to tell when the model actually understands anything, is to be able to test whether it can do so out of distribution. It seems non-controversial that if the model fails on examples that should not confuse a competent human speaker, then the model is not doing something that we would call language comprehension. So to put all of these 3 things together, we have the following definition. We will say that a reading comprehension system has competence in processing a given aspect of the text if it can identify the target information. It does so by relying predominantly on the relevant information and strategies, and it can do so reliably under different distribution shifts, which would not pose challenges to competent human readers and speakers. Now, of course, this definition hinges on human competency, and it could be argued that models could be smarter, should be allowed to be smarter, just because maybe they can see patterns that we don't. But I would argue that we do need to make sure that they are at least better than the human baseline. Because if the model happens to make a good prediction based on the fact that, for example, the amount of cheese produced in the Netherlands somehow correlates with the production of corn in US, that may help us to make the correct prediction in the right case, but this is not the right strategy. So, okay, here's our definition, and what did we do with this? I'm going to share just one example, one case study from this paper, and that is for the reading comprehension questions involving comparison. So, as an example, okay, we have two films. We have an Wikipedia article saying when they were released, and we have the question, which film came out earlier? We have the answer. So just extractive reading comprehension in pretty much squad style. Now, we would assume that the human reasoning steps to answer this question correctly would be to interpret the question, which in machine terms would be like transforming it to a well-formed query. Then it would need to identify the relevant information in the context and use that information, the two movies and their release dates, to perform the target operation, which is comparison between the two dates. So we would say that the model does well if it performs all three of the above. Okay. We collected some data for just targeting comparison questions from Clipboard QA and Wiki multi-hop QA, and we tested them on a bunch of bird family of models of various model sizes. So we use our definition to define which sections of the input the model should rely on. So in this case, that would be the names of the movies, the dates, the relevant parts of the question. We then use different explainability techniques to see whether those parts of the explanation parts of the text actually do get taken into account. And if we see that the answer is yes, then we also want to see whether the model is able to do so out of distribution. So again, our example with Blind Shaft and the Mask of Fu Manchu. Here's the spans that we deem relevant for the 3 expected reasoning steps. For the counterfactual perturbations, we either swap the comparative adjective with its antonym, which also occurs in the training data, or with something that does not. Okay, so the experiments with saliency maps with integrated gradients showed that BERT does not actually consistently attend to the partitions that we deemed important. That's actually consistent with results of another study in which we saw that when people are shown explanations by integrated gradients and asked to tell whether a reading comprehension model is good, then they struggle to be able to tell a good model from a mediocre model, just because it's not obvious what actually is the strategy used by the mediocre model. Okay, so for the in-distribution perturbations, birds are doing reasonably well, except for the small one. So if the label gets altered, the predicted label gets altered as expected. But we do not see this out of distribution. So what seems to be happening is that the model learns not the comparison operation itself, but it learns the specific lexical pattern. If this pattern then predict this entity. And that's, of course, rather disappointing and merits further thinking, which we are coming to. Okay, you may think, okay, this is birds. Birds is like 2018. Maybe the solution is just having an even bigger model. And one reason to say that is that we have seen that no matter how hard we try to create artifact-free training data, we will still have artifacts. There's a wonderful paper by Brno and colleagues, EMNOP last year, showing that basically the bigger the data set, the more likely we are to have unintended spurious correlation, unintended spurious patterns, which the model is, of course, likely to learn. So one argument then would be to just give up on trying to teach the models the right thing and just switch completely to the few shot to the prompting paradigm, in which all the data is supposed to only come from retraining. And then all that we need to do is to provide benchmark data, but not training data, not fine-tuning data. These results would seem to support that hypothesis if we see here that the bigger models, the bigger birds, they are doing better on generalization. So the smallest bird is the worst, and the larger Roberta, which is also trained on more data, it does the best. So it would seem that larger models generalize better. Another study in which we also observed that effect was not for question answering, but for natural language inference. So here on the x-axis, you see the performance of different bird-based encoders of different sizes on MNLI, popular data set, which is known to have a lot of biases. On the y-axis, you see the performance of the same model on Hans, which is an adversarial data set, and the models which learned the biases from the MNLI data set, they would be expected to fail on Hans. And the perfect model would have its performance somewhere in the top right corner. So you see that for Roberta, for Bert, for Albert, the bigger versions of the encoders are consistently doing better on this generalization test with larger, with longer pre-training, though not immediately. So again, that would seem to support the hypothesis that all we need is bigger models. But we do see that no matter how big the model, they do still hallucinate. And more importantly, they fail our tests that we proposed of the performance under distribution shifts, which would not pose challenges to human readers and listeners. So in this case, what you see is the GPT model family of different sizes, their performance on two different tasks, subjectivity and SST. And the problem is here is the variance in the order of prompts which are presented to the model. So the prompts are the same, but simply what is tested is simply the robustness of the model to the variance in the order in which the prompts are presented, the same prompts. And you see that for SST, the bigger models are being more robust. They have less variability, but not for the other task. So just the scale does not guarantee the robustness to perturbations, which should not have made any difference whatsoever. So I guess it's fair to say we are not there yet. And it's not entirely clear how to get there. But I guess fundamentally we need to ask ourselves the question, if we know that bigger data inherently means more spurious patterns, then do we believe that at some model size, the current model would just stop picking up such spurious patterns, even though there would be just more and more of them? So, okay, we don't know how to deal with all this, but I would argue that just having better definitions for what it is we are trying to achieve and how to measure progress might at least help us with the current hype problem, especially for natural language understanding tasks, because they are so underdefined. We are getting the headlines like this. We are getting claims that the models already understand language better than humans. It's getting worse and worse every day. And what's even worse is that all of this hype, it's not just harmless, it creates the impression that we already have a reliable technology that can be put in production. And that's because we are making such claims with respect to completely undefined tasks like reading comprehension. Just as one of the examples of numerous startups based on generative language models, here's a startup that is proposing to help researchers do literature reviews. And this is explicitly based on the question answering. So you can ask a question and the model will do its best to go through its database of scientific articles and list the answers to that question that it found. So you could ask a question like, does social media negatively impact mental health? And it would give you the papers which talk about that and their answers to that question. Now, this sounds great, right? We would all love to be able to skip doing the literature review because it's become basically impossible. But let's be honest, do even human experts reliably assess research questions, claims, and contributions of research papers? And we know the answer is no, because peer review. Everybody who has been through peer review knows that even a human expert might fail to assess either the research question that is actually being asked or the amount of evidence to support that, or all of the above in any combination. So I would argue that we need to stop making broad claims like this model can answer user questions and switch to something more modest, like it can answer user questions about X as long as these known perturbations are not included, as long as this dialect is used, and please note that the factual correctness relies on such and such source. So just to sum up this talk, I would argue that we need to move away from the claims of reading comprehension and general language understanding that we need to work out more narrow definitions for the skills which are being tested. We need to work on better interpretability techniques. So the study that I shared with the integrated gradients are definitely not perfect, and they do not align very well with other techniques like occlusion. We need to come up with better generalization tests for specific capabilities that we're interested in. And as one generalization case study, we need a lot more serious monolingual works on languages other than English, without expectation of mass multilinguality, which basically ensures that only industry labs can do such research, can do multilingual research. In particular, I think for extractive reading comprehension, a lot of the claims about how successful the current NLP models are have been based on the fact that, yes, we have been able to solve data sets like Squad, but this is for a morphologically poor language with fixed word order. So the task is inherently easier for the extractive question answering task is inherently easier than for more morphologically complex languages with free word order. So that's all I have today, and thank you for your attention.
So thank you very much. We have enough time for questions.
I do wish I could see the audience.
Sorry for not seeing the audience. Yeah. So just my question is whether, like you showed that the models that are trained only on unsupervised text only tasks, so these models fail. How about models which are trained on some task-based data like T5 or such, say, more informed models? Do they better in these tasks, or it is the same?
Well, I have personally not worked with those, but I think the point with models like T5 would be to ensure that they can generalize across different kinds of tasks. So you don't want to have the model that can only do language modeling or question answering or something. You want a model that would have different tasks and then inform each other, which would then inform each other. And I think the pattern that we have been seeing so far is that the more you generalize, the more you sacrifice performance on some particular tasks. That's definitely been the case for training on multiple data sets. You get better on average, but then you might sacrifice the state-of-the-art performance on some single one of them, which unfortunately in the current climate makes it more difficult to publish.
Thanks.
Other questions? Okay, so I would like to know whether, well, you mentioned that we compare the systems to some competent human readers. So are there any studies about how much competent are students, or how many of them are competent, or something like that? Because I think that there are quite big differences between competencies of individual students.
Oh, absolutely. And yes, there's tons of research, but that's all in pedagogy and psychology. And I guess we need more of machine learning psychology, where we would be directly comparing and assessing the capabilities of humans and machines, and in which sense it even makes sense to put them head to head. I can share one example from from this quail study that we did, one thing that we found here is that, okay, so this was the first data set to combine text-based, unanswerable, and world knowledge-based questions, right? And we found why people don't usually do that. Usually you see either a factoid data set like SPOD, maybe with addition of unanswerable questions, and then you have the world knowledge-based data set. Data sets like Common Sense QA, and they're usually not together. And it seems that the reason for that is actually this combination is hard for humans, not for machines. So we did an evaluation with not Turkers, with some students who even knew something about the study. And we found that if we present them with all 9 types of questions in the same set, then they will they will struggle to answer common sense questions. They will say for all of them, not enough information, even though they can make a guess in that case. But the models didn't have that problem. And I'm sure that there would be a lot more studies of how humans and machines have different difficulties, with more studies of them head to head.
Thank you. Other questions? Yeah.
Hi, thank you for the talk. It was a very nice and insightful presentation. I was wondering, or first about the context. So it seems that these larger models are somehow exposing a behavior which is like more robust on out of distribution data sets. But the fact is that we do not really like proactively train them to be better on them. So it seems like it's a kind of an emergent behavior that we don't really understand why it's happening. But I'm wondering whether you would have some ideas about like how to achieve this behavior proactively with smaller models, whether there would be some strategies that we know about that enhance the generalization of the model. Thanks.
Thank you. And yes, of course, this is the million-dollar question. I guess at the moment, the research on smaller models that would generalize as well is mostly in the direction of somehow distilling or compressing the larger models. Fundamentally, I guess the answer to the question is what we think is the driver behind this emergent behavior. Personally, it seems to me that the most likely explanation is that the larger models simply were able to memorize more pre-training data, and whatever is in the generalization test set is happens to be more aligned with whatever they happens to have seen, just because they are bigger. In that situation, if that is the driver for this emergent behavior, then it's not really emergent behavior, it's just the fact of having more facts, then I guess we have no hope. We just have to memorize as much as we can. But also it's kind of a dead end, because no matter how much we memorize, there will always be things that we have not seen, because the world is infinite.
Mm-hmm. Thank you. Okay, thanks.
Thanks once again for a very, very inspiring talk. You just mentioned that this quail study is maybe one of the first studies, or the first study which addresses the topic of answerability of the question. And I think it fits very nicely to Brno, where this conference takes place, where Kurt Gödel was born. And he was one who basically made this huge step forward in logics, while asking not only whether the question or the statement is true or false, but whether it actually gives sense, or whether it can be provable or not provable. So my question is, I'm not expert in the field of question answering at all, but I'm quite surprised to hear that practically nobody or few people do the research where the questions are not only supposed to be true or false, or valid or in, or the answers, but also whether they are provable or not, or whether they actually give sense. So is this really like a line of research, or is it just emerging?
So the first data set to explicitly include unanswerable questions, that was the second edition of Squad, I believe. And so far it is the minority. The unanswerable questions have been popping up in different data sets, but as indiscriminate mass. So we don't know which ones are unanswerable, and often we don't know why they are unanswerable. I think so far this is the most complete list of possible problems that there is. Another thing, and I know another line of research that is kind of starting to pick up, I think this in past year, is research on ambiguity. And on the kinds of models and capabilities that would be required to pick the information that is missing in the question, but is available somewhere in the context. So this is being picked up, and I do hope that there will be also more research on pragmatics, on validating the premises of questions and so on. But I totally agree that it's weird that this has not been the focus all along.
Thanks.
Hello, Peter Soika. Being born just a few meters from Gödel's place of birth, I do have a follow-up question to the previous one. In communication, like in academia, it really depends who is speaker and who is the person I pose question to, and how I formulate the question and how the question is being answered. There is most often not really ground truth that would tell you or the both parties whether this answer is valid or not, or because it depends on the values and generalized rules, like my value is the family relation, and that's why I pose the question or answer this in this way. But it cannot be evaluated that it's wrong or right, because there are different points of view on the matter. Yeah. How, and from that perspective, it really matters which kind of bird, how she is trained on, and what values they emerge from during the training, whether at all it's capable of generalizing the values like family relations are important or not, and what do you see whether it's ever possible, or what would be fulfilled to have a better bird that is capable of such generalizations?
I guess the question is, would it be possible to have an extremely personalized bird?
Kind of. Whether the these machines, at least with similar architecture as birds, might have the ability to create latent rules, generalized rules based on the training set that will be used to inference the answers for follow-up questions. Yeah, so the ability to generalize rules on the latent level similar to those, for instance, latent semantic analysis is able to do on the word level, or sentence perhaps on sentence level?
Well, I guess the idea for now is that this is what it is already doing. It is trying to learn some latent patterns from the data that it observes. It's just that it's learning the wrong patterns. Then I guess the question with learning the specific rules that, for example, you would like to see when it's answering your questions, is the question of how close your distribution, your ideal distribution, is to the whatever distribution it has seen, and how can we at least document what that is, so that you know whether it will be of any use to you, right? For that latter question, I think the whole a big part of the AI ethics movement is that is concerned with documenting the data, documenting the speaker demographics, documenting the kinds of biases that go into the model. I think fundamentally this is the goal that they are pursuing, to be able to at least tell when the model is fundamentally useless to you because it has been trained on a distribution that is too different from yours. Does it answer?
Yeah, just last comment. It's all built on the premises that there are generic agreeable premises that holds and that are shared among globally, but that in usual communication is not fulfilled. Similarly, as in Google Gödel theory, he says that whatever contains natural arithmetics, then it has some conclusions of his two sentences. But I'm sad that we are out of time, so I am passing the microphone to Paolo.
Yeah, thank you. So we don't have enough time for questions, but thank you again for the great talk. And we are sorry that we miss you here.
Likewise, I'm sorry to not be there in person, and if anybody deeply disagrees with anything that was said, please let me know.